Sup guys, welcome to today's show. So let's create a compression tool. Let's start by going through some things, how this is going to work on the blackboard. Alright, so let's say this is a file. We can call it penguin.jpg or something. And these represent the data bytes in the file. So 2 of these hexadecimal characters means 1 byte. So the first thing we do is we create 2 very simple lists, where the first is called a block list. And we have an index and a block. And then we have something which I call the unique list. And it has the same shape with an index followed by a block. Alright, so now we divide the entire file in 32-bit blocks. So 8 of these hexadecimal characters. And we treat each of these as a 4-byte integer. So let's start looking at the first here. We will parse each of these blocks one by one. So this block does only exist here, not anywhere else in the file. That means that we're going to put it inside of the unique list. So we type FFFDBE09 and we assign this a 12-bit index. So 000 in this case. Then we replace this by this 12-bit index, and we add a 0 in front just to indicate that this is part of the unique list. So if the 0 in front, we grab it from this list, otherwise this right here. Alright, so let's take the next one, 0, 8, 0, etc. This does exist in several places, which means that we do the same as with the first one, only we put it in the regular block list. So 080 E4 100. And same here, we give it a 12-bit index. And we replace this by this index. And here we set a 1 in the front. The same with this one. And why a 1? Because there is several locations spread over the file, but next to each other there is only 1 occurrence. So that's what the 1 means. But in this case it's more interesting, this 2020, etc. Because we have this block here, but we also have it here and here next to it. So we start the same way. We assign it an index, 001 in this case, and we type in the actual block data. And we replace by the index. But in this case, we do something interesting, because we have 1, 2, 3 in a row. So we just set a 3 here and we delete those all together. So as you can see, if we have several of a block in the file, it will be very much compressed. And if we have several of these in a row consecutively, then they can get compressed all the way to 1/30th or something like that. Because we can go all the way up to 15 here. Let's take one more. So here we have all zeros. By the way, here we have the 2020 again. So this time we use the same index. This is wrong. It should be 1. Yes. So in this case, we do the same thing. We reuse our index 001, and there are 2 in row, so we set a 2 here, and we remove both of these. And we work the same way with these zeros here. So we need third index 000, 000, 000, 000. And same here, we add this index. We have 1, 2, so it's a 2, and we remove these. So as you can see, as long as we have repetitions on a 4-byte level, and even better if we have repetitions next to each other, it will be very much compressed. So this is the general theory of my zip algorithm, which I have constructed myself. And now we're going to write an implementation in C, and see how well this works on different kinds of files. So let's get to it. Did you learn anything useful today? And do you want to support this channel? Go to drbirch.com/support. You can also click the button Become a Member. Thank you for your support. Alright, so welcome back. I have started with some boilerplate, just a make file which does the standard thing, compile all of this. And I have a very minimal C file which does nothing. And then in the H file I have a couple of includes. I have a couple of type definitions for different integer types. And I have some macros for typecasting. That's it. So let's see how this is going to work. One thing which is crucial is that we are able to create some kind of list with all the different 32-bit integers that we read in from the file. Because we're looking, I'm going to divide everything, the entire input file, in 32-bit integers, so 4 bytes each, and I'm gonna look for repetitions. So if we have some value, let's say BC02AA99 in hex, and this is occurring in a lot of different places in the file, then we want to replace this with a reference, basically. So I need to have a data structure containing these mappings. Basically, I want to have some kind of array with structures, so I can map this thing to start with to a number. So if we find one occurrence, we will set a 1 here, and then we increase this whenever we find more. And then I want to sort this list, so I pick the first 4,000 or so with the highest values. So in order to do that, I need to be able to sort a struct, basically. So that's where we'll start. Let's create that structure, and let's create some way of sorting it. Alright, so let's say struct s, and let's see what this is. This is the mapping from the integers to their amount. So this is just a temporary list. So we know which we should focus on. So maybe we can call this an amount list. And I wonder, should we make this a linked list or should we make this an array of some kind? We do need to move stuff around a little bit, but maybe it's easier as an array actually. So let's call this thing amount list. And it's going to have an int32 and this is the value, or the block, let's call it the block. And then we need a counter for the number of occurrences. So let's see how big we need to make this. An int16 should suffice. No, we can't know that. And we might be working with quite big files. Let's make this an int64. So this is the amount. Or we will not have more than 4 billion. Let's make this an int32. It's going to be much more optimized on my machine, which has 32-bit registers. Alright, and if we make this an array, we will not need to care too much about adding anything else here, I guess. So let's start with this thing. And I do want to make this a dynamic array, don't I? Because I don't know how big this is going to be at this stage. So let's say we do that. That means that we need to define a capacity, and we need to define how many items we have. So a length. Something like this. Alright, so we need to create some operations dealing with this thing. So we need to have a constructor function creating this first structure, and we need to be able to add stuff to it, and it needs to be able to grow as well. So let's do that. Alright, so let's see. Let's start with a constructor. So it it's going to return a pointer to an amount list, and this is called make amount list. And it's not going to take any arguments, because this is going to create an empty amount list. And let's also define a zero function that we can use to zero out stuff. So we need to take an int 8 pointer and a size. And we might be dealing with quite big structures, so let's make this an int 64 actually. Alright, so let's create these two functions. Let's also create an alias macro for, I want to have something which is called alloc of x, which is going to currently call malloc of x. Because I might want to use some other memory allocator later on. Let's see if we need that. And let's say we have a destroy of x. And what that does is it runs free of x. Okay, so let's create these two functions. Gonna have a zero function taking an int 8. Let's see. So this is, what should we call this? Destination maybe. And an int 64 size or length maybe. Size is good. And we need to have a pointer, and we need to have a counter. So we set the pointer equal to the destination. We set n equal to the size, and we're going to iterate as long as we have an n, and at each iteration we're going to increase p and we're going to decrease n, and we're going to set p equal to 0. And that's it. So let's create this constructor. We're going to return an amount list pointer, and this is the make amount list. And no argument. However, I want to define as a constant how big this should be and how much we will add at each adding of the capacity. So what should we call that thing? Block size maybe. So how big is reasonable? We're gonna add a lot of stuff to this. Maybe we can say this. So 65,000, basically. All right, so let's say we have an 64 size, and we need to have an amount list pointer. So the size is equal to size of struct s amount list times block size. And let's try to allocate for this. So P is equal to the amount list of alloc size. Maybe we can cast this thing inside of here. Like so. Okay, let's assert that we have a P. Maybe not assert. If we don't have a P, we will return an error instead. Otherwise, we're gonna zero out this thing. And just to be explicit, we're gonna set the length equal to 0, but the capacity equal to block size. And we return P. Okay, so that's easy, just allocating the first one. However, now we want to be able to add stuff to this list. We need to do this a little bit differently, actually. We need to do it in 2 steps. Let's create a structure which is called not an amount list, but an amount entry, where an amount entry contains the block and the amount. And then we delete this, and by the end here we can create a 0-sided array with an amount entry. Data. Okay, this makes more sense. So next we need to have a function for adding things to this. So we can make this a bool. In case it fails, we want to know that. So let's call this amount add, maybe. And what arguments do we need to give this? First of all, we need to know the list, so the amount list in question. And we want to know what amount entry to add. And that should be it, I guess. And let's say we have a void amount delete as well. So this is going to take the index. All right. So maybe we can start with the delete. It's easier because I'm not gonna shrink this thing when we delete stuff. I'm gonna leave the capacity. So void amt delete. We need an amt list. We need an int 64 or should it be 64? The length and capacity are in 32, so let's keep it at that. Maybe we should make this a bool as well, because it actually can fail if we give it the wrong index. Or if we don't have one of these lists. So if we don't have a list, or if we do, but the index is more than the list minus 1, since the index starts at 0. So in these cases, we want to return false directly. Otherwise, there's not much to do other than decreasing. Let's see here. If we remove something in the middle, what do we want to do? Do we actually need to remove stuff? It's a little bit tricky with these arrays, actually. Maybe we don't need to remove stuff. We can add this if we need to. It's not because the delete function is not really compatible with our current design. So let's focus on the add instead. So the add is going to return a bool, empty add, we will have a list, so empty list, and an empty entry E. If we don't have a list, return false. Okay, so first we need to check if we have capacity. Or if we don't have any more capacity. So if the list length is equal to the list capacity, so in that case it's full. Then we first want to check if we are at max capacity. So if the list capacity is more or equal to max cap, whatever that is, I think we can define it as, let's see, so this is the block size. So the max cap so let's say it's the maximum int size minus block size minus 1. That's our cap. And in this case we will just fail. Otherwise, maybe we need to do this anyway. So otherwise we want to increase this list. So after this if statement we should have room for adding the new thing, which means we can let's save the index. So in 32 index, so the index is going to be the current size of the list. And the list data at that index is equal to E. Then we increase the length by 1 and return true. Simple enough. Now we just need to create this increase function. So all we take is an amount list. And if the list if we don't have a list, or if the list capacity is more or equal to max cap, we just return. Otherwise we calculate the new length. So the new length is going to be the current capacity plus 1 block size. And then we can calculate the new size. This is not right. We should have the size of the amount list plus an amount entry, or the size of an amount entry times block size. So same calculation here. So, but not times block size in this case. This is going to be times length. And now we want to reallocate this thing. So we need to have a macro for that. Let's call it R alloc, so we don't conflict. And this is going to take two parameters, x and y. We're going to call realloc of x and y. And I never seem to remember which order they are in. So man3 realloc. So first pointer, then size. Pointer, size. So this is what we want to cast. I wonder how big one of these size t's are. Let's double check that. Four. Okay, so we need to change a couple of things. Our zero function should only be in 32. In 32, in 32. And in our make amount list, we need to make our size in 32 instead. Same with our zero function. Which also means we need to make this quite a bit smaller. So this is 4 bytes, this is 8 total. Basically, we need this number divided by 8 minus the block size minus 1. That should be enough. Where were we? Alright, so we have created a new size. Now we want to set P equal to our R to amount list. And we need to be able to return the new pointer, so maybe we can keep this as a void, but we make this pointer to a pointer instead. So this will be list like this. And P is equal to the amount list of R alloc the list and the size. And then we change the pointer to the new one. First, we need to check that it's okay. So I guess we need to make this a bool after all. So something like this. All right, I think this is going to work. So now we can add stuff to the list and it will automatically grow. Did we update the capacity? So the new capacity should be the length. This. Okay, and let's also create a show function so we can see a little bit about this. So let's say we have something like void show AMT list. We have some kind of identifier and an AMT list. So we print this. And we show the capacity. And we show the length. So something like this. And let's also create some kind of generic macro for the show functions, because we will probably have a couple. So show of x is going to be the generic of x currently we only have one type, So we're gonna return show AMT list. Of the string X and the AMT list of X. Something like this, I think. Probably have a couple of errors that we need to fix, but that's okay. Alright, so let's say we have one of these AMT lists. Set it equal to make AMT lists. And then we show that list. And we destroy that list. Something like this. Alright, let's see if this compiles. Where did my window go? So let's see. List is a pointer to pointer. Did you mean to dereference it before applying? Yes, I meant that. Quite good error message, actually. Alright, so I guess what I need to do is something like this then. And same on line 12. Warning, pointer targets in passing argument 1 of show empty list differ in signedness. Okay. So we need to cast this to an int 8. And it compiles. Will it work? So capacity is this, length 0. Yeah, that's exactly what I was aiming for. Everything worked out pretty nicely, actually, even though I haven't really done it in this way before. Cool. Let's make this a little bit cleaner, though. And this needs to move out. Alright, so let's try adding stuff to this thing. So I want to add something more than this. So we need an int32 counter. Let's just call it n. And let's create some AMT entry. And what does this contain? Block amount. So let's just say something like this, and let's say 5, just so we have something. Let's create a bool for the return value. Or let's not actually. So first we create this list, then we show this list, then we can do this for loop where we set n equal to 0 as long as n is less than so 0x0ff. This is the capacity we have. So let's say 11,000. Plus plus. And we want to do add AMT add lists. We need a name for this. E. So we add the same thing all over again just to see if it works. No, it certainly did not. So where is it crashing? Let's do an strace first. So we're trying to do memory remap. And I don't think that's what's causing it. Let's check an L trace. So the realloc returns correctly, but then it crashes. Okay. So this works, which means we have a P. And then what do? We set the P capacity. And this pointer is pointing towards P. Index list length, list data of index is E. I don't really see why this should crash. But the pointer here doesn't change. Maybe it's not a good way to do this pointer of a pointer thing. Or we should do it everywhere. At least with these add, we actually only need to do it here, I think. Because this is the only thing that makes the pointer change. So let's do the same here. So list length. List capacity. Which means we should not do this. And when we call at, we should provide the reference here instead. Now we only need to change the signature. So AMT add, this should be pointer to pointer. All right. By the way, I forgot one thing. We want to show this list again afterwards. So first we start out with this, then we add a lot of stuff to it. So then we have a bigger capacity, and this is the length. Perfect. Everything works as intended. Yes. All right. I think this will be all for now. After the break, we will continue working on this thing. So, see you just in a bit. All right, you guys, welcome back. So before the break, we deal with the data structures. And before we continue, I'm just going to add one thing to the show function, because the lists are going to be pretty big, so I'm not going to show the entire content. However, I want to show at least part of it. So let's create an int32n. So if the list length is not 0, in that case we want to do a for loop where we go from n is equal to let's say 1, and we'll go as long as n is less than or equal to the list length. So that's one condition. The other condition is that n must be less than 6, let's say, n++. And at each iteration, we are going to print data of n. So let's see. Data of n is equal to, and how do we print this? Maybe we can do it like this. So we start by printing just this thing without a new line at the end. So this is the integer of list length. And then we show the list data of n. And if n is equal to 6, or no, if the list length is more than 5, then I just want to print some dots to indicate that there are more here. So let's see, this is indented 2 spaces. So this should be indented 4, and let's do 1, 2, 3, and then something like this. All right. So now we just need to create a print function for the AMT entry. So this contains a block and an amount. So let's just write a simple one. Show AMT list. No, show AMT entry. So our show function will be an overloaded function that can take many data types. So here we have an AMT entry E. Let's check here that we have an identifier as well. And we'll do the same here. So if we, by the way, this should not be and. So if we don't have an identifier, or well, the IMT entry cannot be 0. So we'll do something like this. Maybe we don't need this. So here we just do something like 1212 EMT entry identifier is equal to, and the first value I want to have in hex, so 0x percent 08x, and the second value should be an integer. So the first is just the identifier. The second is the, let's see, the integer of E. Forgot the quote. And these are called block and AMT. So this is the block, this is the AMT. So something like this. And now we just need to add it to our generic macro right here. So currently we support an AMT list. Now we want to support an AMT entry. Then we call show AMT entry. We should not cast this here. So something like this. Let's try it out. It compiled. That's good. Did it not update? Oh, the length is 0, but here it's not 0. Let's make sure it did update correctly. Show empty list. No, it did not. Why is that? That's weird. It says it updates. Mhm. Very weird. I wonder if it has something to do with me changing this directory to contain a symlink, but it has always worked before, even though. Let's restart it. But let's make copies of these files. So we go into the TMP directory, we open up the zip, I did not intend to open this in Visual Studio. Annoying. Yes, quit. And then we select the entire file contents. Let's make sure it's the right file. Yes. And save. It did react. So did it actually change? Now it seems to work, right? Yes. It must have weirded out somehow. So let's open this H. open this. And now both files are updated. Good. Let's see if it compiles. Show AMT entry is undeclared. Generic statement with no effect. That's a bit weird. Okay, this should be a comma. Main is normally a non-static function. Did I forget to close the function or? Ah, there we go. Now I believe it will compile. But will it work? Sure it does. Very nice. It should not say N there though. And maybe I don't need to add the cast here. Okay, I will not get the index here because N is the variable name, so it becomes part of the identifier here. And it's not much I can do about that, I think. No, but it doesn't matter much, since it always prints the first 5, so this is good enough. Okay, so now we have our data structure and we are able to print it and increase it and add stuff to it. So the next thing I want to do is sorting this thing. But before I do, let's add stuff a little bit differently. So let's see, here we always add the same E. Instead, let's add an EMT entry like this. We can still have the same contents here, because the interesting part, or no, let's not. Let's say 1, 2, 1, 2, 1, 2 plus n. And this one should be something like let's put n here for now. Can remove this E. So now we have a little bit different values inside of this list. So now I want to sort it based on the second argument here, the amount. So how do we do this? Maybe we can do this with some kind of what's it called? Maybe we can pass a function pointer. So let's say we have a sort function which takes some kind of list, and it takes a function where the function compares two entries of this list, and if it returns -1, then we replace them, and if we return 1 or 0, we let them be. And then we can go through this list until it's no longer changing. It's perhaps not the most effective and optimized way of sorting, but it's going to be pretty generic, so I like the idea. Okay. So how to do this? Let's define a data type for this type of function pointer. So let's say we have some sort function. And as input it takes, so this is the function that we pass to the actual sort function. So it's going to take 2 entries. So in our case, these are going to be 2 AMT entries. And it's going to return a signed char. Or maybe we can make it even more generic. So let's say we take 2 entries instead. Let's say we define a union, which we call U entry, and we type def union U entry. And if you don't know what a union is, it's basically like a struct, but it selects one of the contents of the struct, so it can only store one of them. U entry is going to be called entry. And then hopefully we can define it down here. So union U entry. And here we can put all the data types that we will be able to sort. So for now we will only put AMT entry here, but there might be others as well. Something like this. Let's see if this compiles or if we need to do it some... Okay, it looks right. So then we will define this sorting function. So it's going to return a maybe we don't make it assigned char. Let's instead make this some other data type. Let's call it sort result. And the sort result is going to be something like an enum. So enum e sort result. And we can define it down here. I'm not sure if we can do that with enums, but let's try. So enum e sort result. And we're going to have 3 possible results. So either the first one is more than, or it's equal, or it's less than. Does it still compile? Duplicate type def. Oh. That's better. Okay, so let's create the signature for the actual sort function. And let's see how we're going to define that. Maybe as a bool, where true indicates that we are done, and false indicates that we need to sort it again. Or maybe true means that we have that it's changed, something like that. So let's say we have a sort. Maybe the name collides with something. So what should we call it? Zip sort. Because the program is called zip. And it's going to take a list of some kind, point to a list, and it's going to take a sorting function. Something like this. And how can we check if it has changed or not? We need to compare the old and the new. So we need to know the size of this list in bytes. Something like this. And we need to create some swapping function. So let's say we have, no, not among the show functions. Let's say we have some EMT swap. And what should this take? It needs a pointer to an AMT entry and another pointer to another AMT entry. So let's start with that function. So void AMT swap, AMT entry E1, AMT entry E2. We need some temporary variable. So let's start by setting this TMP to E1. And then E1 should be equal to E2, and E2 should be equal to the temporary thing. Something like this. Let's try this function out. So first we create this list. And then we try to AMT swap. And we take the address of the list data 1, let's say, list data 3. So let's wait with this sort function. It worked. So here is number 3, here is number 1. Cool. And I guess we need to make this this swapping function a generic one. So let's just copy this. And we do swap of x. If we have an empty entry, we want to run AMT swap of x. So now we could just replace this with swap. Right, it needs 2 arguments. So we have swap x and y. And we have x and y. This should be a pointer to an empty entry. Okay, still works. Nice. All right, so this function right here, zip sort, so we take a list of something which we need to define, and we can do it the same way as we did here. So this is list. No, this should be the union. So let's copy this right here. And currently we will only support AMT list, like so. All right, so let's create this zip sort. So we take a pointer to a list, we take a size, and we take a sorting function. And I want to try to make this as generic as possible, so it can possibly handle multiple data types later on. So let's say this is the zip sort, and we take a list. By the way, I think I have used the name list. Let's say list capital L. So we have a list, and we have an int32 size in bytes, and we have a sorting function. And how do we do that? We need to traverse this list. So we first need to figure out how big this list is. So let's say all our possible lists have the same structure. They have a capacity and they have a length. And we need to be able to produce a new list. So let's say new is a copy of the current list. And we need to figure out this copy function somehow. The length is the list length. I'm not sure if we can do it like this, but let's say we can. So we do a for loop from n . So n is equal to 0 as long as n is less than list length minus 2 we need to do. Because we need to do minus 1 because of the list length of 1 has an index of 0. And we need to do 2 since we will handle 2 entries at the time, and we don't want to overflow the thing. So n plus plus. So now we want to call that function. So our result is going to be equal to the function of the new list data at n and new data of n plus 1. So the first and the second in the first iteration we compare to each other using this function. And if the first is more than this, we do nothing. If they are equal, we do nothing. But if it's less than, so if this is less than this, then we want to swap the two. Maybe we can call this list copy. But we need to return this new list, don't we? So we can't make this a bool, we need to make this a list pointer. So when we have gone through this whole list, Now we want to compare them. So we want to know if this has changed. So if we run some kind of equal function on the old list and the new list, and if they are equal, we have not changed. Otherwise we have. And if it has changed, we free up the old list and we return the new. Otherwise, we free up the new list and we return 0. All right, I think this might work. It's a quite elegant construction. Do we need this sized thing? No, I don't think we do. Okay, so we need to create this list copy. Let's update the signature before we forget. So we don't need this in thing. Maybe we can put all the sorting functions close together. So let's say so list copy, it takes a list pointer. So first we create a new list. And how do we do that? How do we do that in a generic kind of way? Maybe we can say this is an AMT list for now. So then we just call make AMT list. All right. So now we just need to add all the items. So we do a for loop where we set n equal to 0. We go as long as n is less than. As long as it is less than the list length. But what if the length is 0? In that case, we just want to return this new empty list. So if this is 1, for instance, then we will at least do it once with this and plus plus. And we want to run AMT add, and we provide a reference to our new list. And what do we want to add? Well, we want to add the list data of n. And then we can just return the new one. Okay, so it was easy to make this AMT list copy, but how do we make it generic? I guess we could do the same trick as we have done here. So if we have an AMT list, we want to call AMT list copy of X. So something like this. Maybe this should be -1 after all. But we need to do some check, because if the list we are trying to sort only has one item, in that case we want to return. So if list length is less than 2, we return 0. Okay, I think this might work. I'm a little bit worried about the data types, but we'll see what GCC says. Is there anything else we need to do? Well, with this equal function, we need to write one of these. And let's do the same as with the other ones. We start by creating an AMT list equal. And we need AMT list L1, AMT list L2. And if we don't have one of these, let's return false in that case. Otherwise, what do? First, we need to check if their length differ. So if L1 length is not equal to L2 length, because if their length differ, they are not equal, so we can return false. So now we at least know that they have the same length. So let's do a for loop where n is 0, n less than L1 length, n plus plus. And let's say the result is true. And if L1 data at n, I wonder, can we really no, we can't really do that. Let's do something like this. If L1 data at n dot AMT is equal to L2 data at n AMT, and L1 data n block is equal to L2 data n block. So if both of these are equal, we do nothing. Otherwise, we set res is equal to false and we break. By the end, we return res. This should work, I think. And now we just need to make this generic. So this is going to be list equal of x and y if they are empty lists. We call empty list equal of x and y. Okay, do we have all the moving parts now? Let's see if GCC allows this kind of magic. Conflicting types into list copy. Right, here we take a list. This should be changed to an empty list. Sort fun. Conflicting types for zip sorts. So we have a list and a func. Ah, here I made a bool. So let's see. List zip sort, list sort func. Ah, I have the star here. I wonder which is correct. List has no member named length. Okay, I was a little bit afraid of this. So how do we access these things? Maybe we can wait a little with that. And let's say we make this an empty list. Let's say we have one called list as well. Let's rename this. Will this work? Turn list 0. This should be a pointer. Called object func is not a function or a function pointer. Maybe this should just be like this. It's also always a little bit tricky with those function pointers. Let's remove it here as well. Incompatible type for argument 1 of func. Expected entry. The argument is KMT entry. So let's cast that thing. Cannot convert to a pointer type. Res is a sort res. And what does this return? Type def sort res. But why does it want to be a pointer? So what if we make it an int 8 instead? And we make this an anonymous enum. Is that possible? Tricky, tricky. wonder why it wants it as a pointer. But let's say it is a pointer, which would turn this into 1. Let's say we don't type def this. We type it in explicitly. So this will be an int 8. And it's going to take a sort an entry. and another entry. And here we will do int 8 func entry. Cannot convert to a pointer type. So why does it want it to be a pointer type? Hmm. And if we make it a pointer, same error. I don't understand. Why does it think it's going to be a pointer type? Okay. Type name declared as function returning a function. What if I don't care about the return value? Then what? Uh, so it's not the return value that's the problem. We can't even call this function. Let's change this to void. Maybe it's the argument it's referring to. Yes. Okay, I have been troubleshooting the wrong thing. So let's move this back. As an argument, it fooled me because it highlighted the name of the function, right? So I thought it was the function call of the return value, which was the error, but it was the argument. All right, so a sort func is what we want to have here. So type def int 8 sort func entry. So here we have a sort func. And this should just be entries, not entry star. So now we're down to the swap function. And what we give is new data n. New is an empty list. Right, here we should provide a reference for this. It compiled. Pretty cool. Let's see if it actually works. We need to create one of these sort functions though. So let's see, int 8 sort AMT or AMT sort. And this is going to take 2 AMT entries. So int 8 AMT sort, and we're going to have an AMT entry E1, AMT entry E2. So if E1 dot, and we want to compare the amount. So if E1 amount is more than E2 amount, in that case we return what do we call it? Greater than, more than, and more than, else if E2 AMT is equal to E2 AMT, case we return equal, and otherwise we return less than. So we show this list first, and then we try to sort it. So we run zip sort, and the list is called list, and the sorting function we called AMT sort. Maybe we need to do this. Passing argument 2 of zip sort from incompatible pointer type. It is okay, so the function itself has the wrong type. So let's say these two are entries. something like this. Something like this, maybe. Assignment to int32 makes integer from pointer without a cast. That's a problem in my main. So this result, it will return the new list. That's right. Something like this. Okay, it compiled. Let's see what happens. So this is the first list. And after we have gone through it, it becomes this. So it's a little bit more sorted, right? And that's the point. So this is an iterative process. If we were to run through this one more time, I guess we would get an even better result. But why does it crash down here? We destroy the list instead of the new. So let's try doing this one more time then. This should be the new one. Alright, so first we have this, then we run through the list and we get this, then we do it again and we get this. So 2, 4, 5, 6, 7. So it does sort it, but where did the 1 go? It does still have the same length. So it almost works, but not quite. Maybe it's the copy function which messes up something. Or maybe it's the show function, perhaps. And it's 1. Let's show from N0 instead. So we have 0, 3, 2, 1, 4. Here we get 3, 2, 1, 4, 5. 3, 2, 4, 5, 6. Let's go to the swap function. Hmm. So why does it swap 0 and 3? They are in the correct order already. Did I get it mixed up somehow? Right, this should probably be more than. So we're swapping 3 and 2. So 2 is on top. We're swapping 3 and 1. Swapping 2 and 1. That kind of makes sense, right? Let's see what the result is now. Zero 3 2 1 4 0 2 1 3 4 0 1 2 3 4. Ha! Beautiful. And what happens if we run this one more time? Huh. Here we end, because we try to sort this list, but it's already perfectly sorted, so we end. So now everything works exactly as I'd hoped. Maybe a little bit less generic, but we have to live with that. So we have successfully created a pretty advanced sorting function. And I think this will be all for today. In the next episode, we're going to start building on the actual compressor. And I really hope you like this episode and want to follow along with this project. Please like and subscribe. And thanks for watching. Thanks for today.